try and understand what is a context-free grammars. So this is the definition for a context grammars. A context-free grammar is a type of formal grammar used to describe the syntax of a programming languages, natural languages, and many artificial languages. So this is the definition of a context-free grammars. A context-free grammars is a formal grammars defined by four tuples. Basically, it is represented as VTPS. So V is a finite set of non-terminal symbols and T is a finite set of terminal symbols and P is a production rules and S is a start symbol. So this is the definition, formal definitions of a context-free grammars. It is basically made up of four attributes. So let us go to the problem statement and let us try to write the context-free grammars for a given set of a problem. So here any number of A's, let us try to write a context-free grammars for any number of A's. Here is a problem statement that we can see that L is equal to A power n greater than or equal to 0. Where the language is nothing but it will accept any number of A's including empty string as well. So the grammar is, we will be writing like this. So let us see that how we should be able to write the grammars. So here any number of A's means it is equivalent to A star. The regular expression is A star. A star means you can have any number of A's. Empty string, single A, 2 A's or 3 A's or any number of A's for this particular matters. How we should be able to write a grammar is, as we mentioned earlier from the definition, it is made up of four attributes. Terminals, non-terminals, start symbol and the production rules. So this is a start symbol. S tends to, this is the rules, production rules. S tends to AS. So here S tends to AS or an empty string. So this will take any number of A's. So in order to validate this one, whether the grammar that is generated is generating any number of A's means, say suppose if at all you want to generate only one A's, okay, or an empty string. So S will take an empty, okay. So this is where you can see that very first example, it will take only empty. The next example is S will take at least one A. S tends to, the derivation is S first will be having the first rule that S is equal to, yeah, first one is it will start with S and then what I am going to be doing is S will tends to AS. Then S will take an empty string. So S will take an empty string, apply the empty string and the resultant you will be having 1A. Similar fashions, if at all you want to have a 3A's if at all you want to generate a 3A's, then what I will do, the first rule is S tends to, this is how I am going to be doing the derivation. S tends to AS and once again S tends to AS. And once again S tends to AS and substitute in the last stage, you substitute with an empty string. So this is going to be generating any number of A's. Or else there is one more way of validating using a parse tree. Okay, using a parse tree. So using the parse tree, how we should be able to generate is, here we have a tree. Like, so first it will start with a root node called S and it has got two branches, that is AS. Say suppose we want to generate it for 3 A's means how we will be able to generate a parse tree is S tends to AS and S tends to AS, S tends to AS and S tends to epsilon. So if at all we see the root node, you have 3 A's. So this is how we should be able to validate that the given grammars is correct or not. So this is how we should be able to generate any number of A's. Similar fashions, let us see the one more problem. So this is any number of A's. So S tends to AS or empty string. So this is how the derivations would be done. S tends to AS, S tends to S, once again AS, S tends to AS. Any number of A's you should be able to do the derivations. Similar fashion, at least one number of A's means the grammar would remain the same except the terminator symbols would be A. It is not empty characters, it is an A. Okay, similar fashions, if at all we want to accept any number of any string over sigma is equal to A comma B, this is nothing but A plus B the whole star. A plus B the whole star means AS or BS or empty strings. So it will take any number of A's, any number of B's or an empty string as well. So this is how you should be able to write for n number of A's and B's. Similar fashions, if at all we have to write A power n and B power n. So this is quite interesting. A power n, B power n greater than or equal to 0. So it is A followed by B's, wherein there should be equal length of A's followed by equal length of B's. So that is where you can see the same power is used, n and n is used in order to measure the length of it. So now to write down context free grammars for A power n and B power n, where n greater than or equal to 0, it is very simple. So how we should be able to write it? It is, we have a problem statement A power n and B power n, where n greater than or equal to 0. So for this one, the grammar would look like this. S tends to A, S, B or epsilon, because n greater than or equal to 0. So the minimum string would be the empty string only. So let us take 2 A's and 2 B's and let us try to validate A, B, B. So for an A, B, B, how we should be able to do the validations is using the derivations. We should be able to derive like this. So you can see this. This is where you should be able to see that S tends to A, S, B. A, B, B, you can see S, first the rule will be A, S, B. Second rule is once again recursively we are going to be apply ESB, and then S will tends to an epsilon character. So whenever you want to halt, you apply the epsilon characters and derive 2 A's and 2 B's. Similar fashions we should be able to apply the parse tree as well. S tends to A, S, B, and S tends to A, S, B, and whenever we want to halt it, apply the empty string and just see the root node. It is A, B, B. So you have A, B, B. So this is how we should be able to validate the given set of strings.